So in some of the processes, the absorbed energy is given up in form of heat to the surroundings, and in some of the processes it is emitted as radiation. That means when the molecule will again come back to the ground state from the excited state, so it can emit the energy, it can lose the energy, the absorbed energy, it can lose the absorbed energy in the form of heat or in the form of radiation. When such a that process is known as relaxation. When the molecule will undergo transition from excited state and come back to the ground state, that process is known as relaxation. That means the molecule will undergo relaxation either by emitting heat or by emitting radiation. When such a relaxation is accompanied by emission of radiation, it is called as luminescence. So there are two types of luminescence phenomena are there. So the first one is phosphorescence and the second one is fluorescence. First one is fluorescence and the second one is phosphorescence. So two different types of luminescence phenomena are so there. So that is fluorescence and phosphorescence. So the fluorescence and phosphorescence that arise from the excited state generated by the absorption of electromagnetic radiation. Fluorescence, so first we'll discuss what is fluorescence and what is phosphorescence. Fluorescence is the emission of the visible light by a substance that has absorbed the light at a different wavelength. Again, fluorescence is the emission of visible light by a substance that has absorbed light of different wavelength. So this emitted photon has a longer wavelength. Phosphorescence is related to fluorescence in emitting a photon. However, a phosphorescent material does not immediately re-emit the radiation it absorbs. That means as we know that the lifetime of a molecule in the excited state is very short, that will undergo relaxation process. The relaxation process can be done by emitting heat or by emitting radiation. If the molecule will undergo relaxation by emitting radiation, then the radiation, then the phenomenon is called as luminescence. Luminescence is divided into two types, that is fluorescence and phosphorescence. So in fluorescence, the molecule will emit light in the visible region, in the visible range, and in phosphorescence that is also emit light in the visible range, but it will take some time. Fluorescence will take place immediately when the molecule will move to the excited state. Immediately it will come back to the ground state by emitting light, that is called fluorescence. But in case of phosphorescence, from excited state it will come back to the ground state after some times, not immediately. As the excitation of the molecule is due to absorption of a photon, these type of luminescence are called as photoluminescence. So because we have already discussed that initially the molecule will undergo excitation by absorption of photon, so that's why that process is called as photoluminescence. Now coming to chemiluminescence. Chemiluminescence, another phenomenon that falls in this category of the luminescence. This refers to emission of radiation during a chemical reaction. So what is photoluminescence? If the molecule will absorb electromagnetic radiation from the UV region, that will undergo transition from ground state to excited state, and again that will come back to the ground state by emitting light energy. So if it will immediately come back to the ground state after excitation, that is called as fluorescence. If it will come back to the ground state after some time, that means a time period will be there, that is known as phosphorescence. And both the phenomenon are known as luminescence. But initially the molecule will be excited by absorption of UV visible light, so that's why that process is called as photoluminescence. But in some cases another type of luminescence is there, that is known as chemiluminescence. The chemiluminescence takes place when there will be chemical reaction takes place between the molecules, and the molecule will undergo excitation. So this refers to emission of radiation during a chemical reaction. However, in such cases, the excited state is not a result of absorption of electromagnetic radiation. So the molecule will undergo to the molecule will go to the excited state by chemical reaction, not by absorbing electromagnetic radiation. That's why that is called as chemiluminescence. Here, one example of chemiluminescence process is so there, that is the oxidation of luminol. So this one is luminol. Luminol will undergo oxidation to form aminophthalate ion, and this aminophthalate ion will emit visible light. So an aqueous solution of luminol is oxidized by a solution of sodium chlorate and gives out blue glow without increase in temperature. That means without any increase in temperature, the substance will give blue glow. Luminol is oxidized to aminophthalate ion, which is produced in an excited state and emit the blue light on dropping to the ground state. So this is the reaction of the chemiluminescence process for luminol. The process involved in the excitation by radiation and the radiative emissions can be understood with the help of a Jablonski diagram. So the total process of initial excitation and coming back to the ground state by emitting energy, so that can be explained by a very renowned method that is known as Jablonski diagram. So here we will discuss Jablonski diagram. That is a very important long question. So the Jablonski diagram gives a representation of ground state and excited electronic state of molecule and the process associated with absorption and emission of energy. So a typical Jablonski diagram is given here. You can see, so this is a typical Jablonski diagram. So first we should know what are the different energy levels. So the initial energy level, so these are called as ground state of the molecule, ground state electronic state. So these are referred to as S naught. And here these are the different excited state, S1, S2. So these are the different excited states. So why that is called as S0, S1 and S2? Because in the ground state the molecule is in singlet state and this one is T1. So that is S1 means singlet ground state, S0 means singlet ground state, S1 means singlet excited state, S2 means singlet excited state, T1 means triplet excited state. So these are the singlet excited states and the T1 is the triplet excited states. So now coming to the procedure. The straight lines at the bottom of the figure represent the ground state, and ones in the upper portion indicate the excited electronic states. To the begin with, the molecule is in the electronic ground state. So first we will start the molecule is in the electronic ground state, that means in S0 or S0 state. In this state, the molecular orbitals are occupied by 2 electrons because the capacity of every molecular orbital that contains 2 electrons. And we know that according to Pauli's exclusion principle, the spin of the 2 electrons in the same orbital must be antiparallel. This implies that the 2 electrons, if the spin of the first electron will be clockwise, the spin of the second electron will be anti-clockwise. So the 2 electrons present in the ground state is in antiparallel manner according to Pauli's exclusion principle. So the total spin of the molecule is in the ground state. That means the total spin of the 2 electrons present is in the ground state molecular orbital will become 0. And we know that the total spin, so that is 0. And that's why that is called as S naught. But the multiplicity, the multiplicity can be, the formula of multiplicity is 2s plus 1. So this is the formula of multiplicity. And in the ground state, as the 2 electrons present in the orbital is in antiparallel manner. Antiparallel manner means if one electron is in clockwise manner, another electron will be anti-clockwise manner. So the total spin will become 0. As the total spin of the 2 electrons present in the ground state molecular orbital will be 0, so the multiplicity will be 2 into 0 plus 1, that is equals to 1. That's why this state is called singlet state. So the singlet state can be labeled as S0 or S0. The electronic spin in the excited state achieved by absorption of radiation may be either parallel or antiparallel manner. According to this may be a triplet that is in parallel manner. This may be a singlet that may be antiparallel manner. So in the ground state, the two electrons will be in antiparallel manner. That's why the multiplicity will become one. That's why that is called singlet. But in the excited state, the two electrons may be present in antiparallel manner. The two electrons may be present in parallel manner. If the two electrons present in antiparallel manner, then the spin will become zero and the state is said to be singlet state. But if the two electrons will present in parallel manner, then the total spin will be half plus half, that is 1. That means S equals to 1. So 2 into 1 plus 1, that is equals to 3. That is called a triplet state. So accordingly, this may be, so if the two electrons in present in the excited state will be in parallel manner, that is called a triplet state. That will be so represented as T1. And if the two electrons in the excited state will be present in antiparallel manner, that is called singlet state, that is so represented as S1. So you can see in the ground state, the two electrons will be in antiparallel manner. Antiparallel manner means one having clockwise spin and another having anti-clockwise spin, and hence the total spin will become plus half minus half, that is equals to 0, and hence the multiplicity will be 2 into 0 plus 1, that is equals to 1. So in the ground state, that is called the singlet state. And here this is the singlet excited state. So this is one of the excited state where the two electrons is in antiparallel manner. So the total spin similarly becomes 0 and the total multiplicity will become 1, that is called singlet excited state, that is S1. And if the two electrons present in parallel manner, that means the two electrons will be in clockwise have clockwise spin, then the total spin of the two electrons will become plus half, that is equals to 1. And hence the multiplicity will become 2 into 1 plus 1, that is equals to 3. So that is called excited triplet state T1. This is excited singlet state S1, and this is excited singlet this is ground singlet state. The first one is ground singlet state S0, and here the molecule will absorb electromagnetic radiation from the UV visible region that will undergo excitation. So if in the excited state, the two electrons present in the molecular orbital will be in the antiparallel manner, then that is called singlet excited state S1. And if the two electrons present in the excited state in parallel manner, then that is called triplet excited state T1. So the energies of the two excited spin states are also different due to different in interaction between the electrons. The energy of the triplet state usually is slightly lower than that of the singlet state. In the Jablonski diagram, the two excited states S1 and S2 and the singlet states are shown. So now coming again to the Jablonski diagram. So in the Jablonski diagram, you can see, so this is the ground singlet state S0. These are the ground singlet state S0, and this one is excited singlet state S1. This is another excited singlet state S2 having higher energy, and this is excited triplet state T1 having slightly lower energy than the first excited singlet state S1. Now coming to the process takes place in the Jablonski diagram. First one is excitation, first one is activation. So initially the molecule will present in ground state S0. This one is the ground state, the bold line, that is the ground state S0. Initially the molecule will present in ground state S0. So if the molecule will absorb energy from the UV visible region, that will undergo transition from the ground singlet state S0 to either S1. So that will undergo transition to either S1 or undergo transition to either S2, that depending upon the amount of energy absorbed by the molecule. So that process is known as activation. Now coming to the next process is deactivation. So after activation, that means after the excitation from S0 to S1 or S2, the molecule is in excited state, and the lifetime of the molecule is in the excited state is extremely small, very less. That will again come back to the ground state, and that process is known as deactivation. The deactivation can be takes place in two ways. The first one is non-radiative deactivation. That means the molecule will emit heat energy and come back to the ground state. That is called non-radiative deactivation. And the another type of deactivation, that is known as deactivation. In the radiative deactivation, the molecule from the excited state coming back to the ground state by emitting light energy, by emitting radiation, or by emitting electromagnetic radiation. So that is called radiative deactivation. In the non-radiative deactivation, that means the molecule in the excited state will come back to the ground state by emitting heat energy. So the non so radiative deactivations are divided, can be classified into different types. The first one is vibrational relaxation. In the higher vibrational levels of an excited state, the molecule rapidly loses its excess of vibrational energy by collision with other molecules and falls to the lower vibrational energy level of the excited state. In this non-reductive mode, that is called vibrational relaxation. So the energy lost is dissipated as heat to the surrounding. In principle, the non-radiative or radiation-based deactivation may also lead to the relaxation of the S1 state to S0 state. However, such relaxation is quite slow. So this is the S1 state, that is the ground electronic state, which is the singlet state, and this is the S0 state, that means the ground electronic singlet state. And between this ground electronic singlet state, number of vibrational energy levels are there. So these are ground state vibrational energy level. Now coming to the next excited state, that is called S1, that is the excited singlet electronic state. Within that, some vibrational energy levels are there. These are called excited vibrational energy level. Now S2, that is another excited singlet electronic state. Within that, some vibrational energy levels are there. So when the molecule is in the excited state, that if that will undergo radiation less transition or non-radiative transition, means due to collision with other molecules, the excited molecule will lose some amount of heat energy, and that will undergo transition within the same electronic excited state, but between the vibrational energy levels. And that process is known as during that process, the molecule will come back to the ground state, but that process is extremely slow. Now coming to another type of relaxation process, which is non-radiative. That means by emitting heat energy, once the molecule that has excited to the electronic state, that is S2, which is higher than S1 state, if the molecule will undergo transition from S0 state directly to S2 state, if the molecule undergo transition from S0 state to S2 state, that means S2 state means the second excited electronic state, which is singlet state. Second singlet excited electronic state.
good, good.